All right, this podcast, we're going to talk about routing and routing protocols. If we recall from our Layer 3 podcast, routing is the process of getting the datagram one step closer to the destination. So we don't know exactly where it needs to go. We just know, we don't know the entire path it needs to follow. We just know how to get it one step closer to where it needs to go. So if we recall what we talked about in the other podcast, here's what end-to-end IP is responsible for end-to-end delivery. So from a 20,000 foot view, we send something into the cloud and it comes out the other side. But we said more specifically, there's a bunch of routers in there that do their routery goodness and magic to make it happen. So we're also going to review host routing, right? We said a host consists of routes for connected networks and a default route to the gateway. How does a host decide how to send the packet? Well, if it has a connected route for that datagram, it will send it locally. Connected means the host is connected to that network. If it doesn't have a connected route, then it will send it to its default gateway usually. Here was our picture for host routing. We had host on the bottom, needed to send to the host on the top. They're on the same network, so it would send it directly. Otherwise, if it needed to send something out to the cloud, it would send it indirectly. It would send it to the router, and the router would take care of delivery of that datagram. For a router to route a packet, we had the same slide before. The router will remove the datagram from the layer 2 frame. It will check the destination IP address and make a determination what to do with it. If the packet is destined for the router, for example, somebody's SSHing into the router, then it will deliver it up the stack to the next layer, TCP, and then the actual SSH server, if it's SSH. If it's for a connected network, the router will deliver it out to that network, to the destination host on the network. And if it's for any other destination, then the router will check its routing table and send the packet on its way. And I said, don't worry about routing tables. We'll talk about those later. So guess what? It's later. We're going to talk about today how routers decide what to do with packets and how routing tables get built. So we talked about this generic example of a routing table with a few networks. We said that the router has a connected route for every network that it's directly connected to. Those have the Cs. And then we said a router will probably have a static route for the default gateway. All zeros route goes out to the cloud. So let's talk about how that actually happens. Here's a output of the show IP interface brief command, which is a command we will run a lot on our routers if you're having problems and you ask me for help. I'll either ask you to run that command or I'll ask you to run show IP route. Usually those are the first two commands I run. If you run show IP route and it doesn't have everything it's supposed to, then I'll probably tell you to run show IP interface brief. In this case, the output of this command, it shows that we have two interfaces that are in the up and up state. We're connected to the 192.168.2.1 2.something network with the IP address of 2.1, and we're connected with serial 1/0 to 192.168.1.1. These interfaces are in the up and up state. When I say that, you look at these two status over here, and the protocol status is the line status. Protocol is a protocol status. Up and up means it's working, and that means that there should be a connected route for this network in the routing table. If you do not have your interfaces in the up and up state, there will not be connected routes in there. The administratively down means that the interface has been shut down. By default, the router interfaces are in a shutdown state. You need to do a node shutdown to bring the interface up after you assign an IP address to it. So if you are trying to get things to work and you do show IP route and things don't show up that you think should show up, then the next step would be show IP interface brief to make sure, or that sounds right. That didn't sound right. To make sure your interfaces have IP addresses and are in the up and up state. So assuming your interfaces are in the up and up state, then you'll have a routing table that looks something like this. I have a connected route for the 1.0/24 network. That was the network of my serial interface. I have a connected route for the 2.0/24 network. That was the network of my fast Ethernet interface. And I also have this third connected route for a /32 network. You can ignore that for now. That's not in there. That's in there because of the side effect of something else. We're using PPP on the serial interfaces, and that's something that PPP does in this case. But you can ignore that for now. You don't always get that extra connected route. So those are the connected routes. We talked about default routes. That is where we need to send traffic that we don't know what to do with. Two places you see that here. We see a static route with the all zeros, which means this is the default route, and it says it's going to 192.168.1.2, right? The other place we see that is up here. It says gateway of last resort is 192.168.1.2. So that is the two different places we can identify the default route for this router. The command at the bottom is the command you would use to enter a default static route on a router. You will be doing this command pretty much a lot to make sure things work properly. So there we have IP space route 0.0.0.0.0, 0.0.0.0.0, 192.168.1.2. We'll see some more examples of this in a minute, the IP route command, and I'll talk more about it then. And here we are, more examples. So here's a different routing table where I have some connected routes and some static routes. Here I have the same connected routes we had before, 1.0 and 2.0, and then I have some static routes for some 10 networks, 192.168.10.0, 192.168.10.64. First, let's talk about how those networks got put in there. I ran these two IP route commands you see at the bottom to enter those networks in there. If you look at the first one, it says IP route, and then the first part of that command is the network address that I'm concerned with. So in this case, I have 10.64. The second part of the command is the subnet mask I want to apply to that network. And then the third part of the command is the is the router that I need to send packets to when I add the static route. So basically I'm saying, hey, if you get any packets for 192.168.10.64 with this mask, which is a /26, send them to the router that lives at 192.168.1.200. Right? So this would be any destination IP addresses from .64 to .127 would get routed to 1.200. The second route, syntax is the same. IP route, network address, subnet mask, next hop. This says anything that is 192.168.10.0, 255.255.255.128, send that to 192.168.1.100. So essentially that is saying anything that goes from .0 to .127, I want you to send to 192.168.1.100. So if you did your subnetting and you are paying attention, then you may be asking yourself right now, well, 192.168.10.0 with that that subnet mask is a 25-bit prefix. It's a /25, so that goes from 0 to 127, and then the .64 with the net mask we gave it goes from .64 to .127. So those two statements overlap. So is that going to mess things up? And the answer is no. The routing table searches the routing. The router searches the routing table in a specific method so that it finds the most specific matches first. The most specific matches would be the match with the longest prefix length, which would in turn give us the shortest network size. So let's talk about what that means for a second. This bottom route we entered goes from 0 to 127. The top one goes from 64 to 127. So if we did not match the most specific route first, or the longest prefix length, or the smallest network size, then we would not get this route if we match the other route first. So let's look at a couple of examples of what would happen with this particular routing table. So say, for example, we need to send a packet to 192.168.1.10, right? We're searching our network address. The way it's going to search is going to start with the longest prefix link. So it's going to be like, okay, 192.168.10.64. No, the 192.168.1.10 doesn't match that. It's going to check this one. 192.168.10.0. No, 192.168.1.10 doesn't match that. And then it's going to start checking the /24s, and eventually it will match this one. 192.168.1.10 will match that. All right, so let's say we have a packet that needs to go to 192.168.10.75. First one it's going to actually check is going to be this one here, 192.168.10.64, since that's the most specific match, because .75 is in that network. So that's the router's going to find that route, and it's going to route it out to 192.168.1.200. Let's have another example. 10.200. What's it going to do with that? Well, it's going to check this 192.168.10.64/26 is 10.200 in a part of that network. Well, if you did your subnetting, you know that 10.200 is not a part of that network. So we'll check the next one, 192.168.10.0/25. 10.200 is not a part of that network. So then we check 1.0/24, no, not there. 2.0/24, no, not there. And that is going to match the default gateway. So a packet destined to 192.168.10.200 will actually be sent to 192.168.1.2. So that is how the router decides what to do with packets. It searches the longest prefix length first. And actually, I lied to you guys a minute ago. It would actually hit this 32 first. This is the most specific one. It would hit that one first, and then the 26, and then the 25, and then the 24s, and then the default route. So that's how the router searches the routing table to make its routing decision. We have the idea of static routes we just talked about. So in this case, we have two PCs with a bunch of routers in between it. We could very easily set a static route that says, hey, if you need to get to that network, send it to this router. And on this router, we could say, hey, if you need to get to this network over here, send it to this router. And we can figure that all statically using these static route commands we learned about, right? And that would work okay, because if one of the routers went down, it wouldn't matter because there's no path for the packets to take when that router is down. But if we get a more complex network where we have more routers, then using a static route like we just did doesn't make a lot of sense. For example, for a datagram to get from this PC to this server, we send it to this first router. Well, then that first router has three choices, right? If we put a static route in that says, hey, send it to this router, and then this router goes down, well, it's going to break the path, even though we have two alternate routes we could use, because we have a static route in there that says, hey, send it to that router. So that's one of the reasons dynamic routing protocols exist and why they're better than static routes. We have two main objectives for a dynamic routing protocol. One objective is to build a loop-free routing table. Why do we want it to be loop-free? Well, we talked about the time to live field on our IP datagrams. If we are going around in a circle, we will eventually kill the packet and discard it. Also, routing a packet in a loop implies we're routing it across the same links more than once, and that's not a very efficient use of our resources. So we want to have loop-free routes. They do that by following these steps. They share the local topology with other routers, so we have our connected routes that we know about. We need to share that information with other routers, and we learn remote topology from other routers. And we also even share information we learn from other routers with other routers. So I left that step off. But yeah, we share our information, we learn information, and then we share all the information we have. Once we share all the information, each router picks the best route and puts it into the routing table. And how does it pick the best route? Well, that varies by which routing protocol we're using, and we'll talk about some of those routing protocols in a little while. The second thing a routing protocol needs to do, it needs to detect changes in the topology and update the routing protocol, the routing table appropriately. We had this idea of convergence. That's how long it takes to detect and correct issues. So we want routing protocols that converge quickly because we want them to figure out that things are broken and fix it quickly. And how do routing protocols detect the topology changes and update the routing table? Well, that varies depending on which protocol you're using. Two main types of routing protocols: interior gateway protocols. These are used inside a single autonomous system. An autonomous system can be thought of as like an organization. So like HACK would be an autonomous system, and Blue Cross Blue Shield of Harrisburg, I don't know if that's even a real place, would be a autonomous system. And I don't know, I can't even think of places right now. City of Harrisburg would be an autonomous system probably. And the common interior gateway protocols you will run into are RIP, OSPF, and EIGRP. Exterior gateway protocols are routing protocols that share information between autonomous systems. So this is how we get the traffic actually across the internet between the different companies or different end users. And normally BGP is the primary protocol used for that. For EGP, exterior gateway protocols, BGP is the main protocol for that. So let's look at this dynamic routing protocol, dynamic routing table. If you look at the command up there, it says show IP routes. That's a command that will show you routing table. We have connected routes, right? We have a connected route for the 1.0 network. I have a connected route for the 11.252 network, and I have a connected route for the 21.0 network. I have learned routes for the 11.0/27 network. I've learned a route for the 12.0/24 network, and I've learned a route for the 22.0/24 network. Let's look at a few more things in here. The letter on the side tells where the route came from. So C means connected. R, if you look up here, R stands for RIP. So these routes were learned with the RIP routing protocol. Inside these square brackets, we have this first field is the administrative distance. The administrative distance is kind of a measure of the goodness of a routing protocol, if you will. So routing protocols have different features, and some of them work better than others. So the administrative distance gives the router an idea of the believability of the route. So if you have multiple routes, if you're using multiple routing protocols and you have multiple routes, you want to believe the route that came from the better routing protocol. So the administrative distance is a measure of how good a routing protocol is. The next value after the slash is the metric. The metric is what the routing protocol uses to determine which route is the shortest. If you look at a internetwork, and there are multiple different ways to get to multiple places. Let's go back to my other slide back here. So I could get from here to here straight, 1, 2, 3, 4 hops, or I could get there this way, 1, 2, 3 hops. So which one will be faster? Well, it depends on a lot of things, but in the case of RIP, it just uses a hop count. So in RIP, my metric on this router for networks over here would be 1, 2, 3 hops. So the hop count, the metric is I said what the metric was. RIP uses the hop count for the metric regardless of link speed. This next thing tells what the IP address of the next hop router is. This is a timer used with RIP, and this tells which interface the traffic should be sent out. So we talked about RIP. It is a distance vector routing protocol. That means it uses a hop count for its metric. The convergence on RIP is slow. It uses timers to detect failures, and it requires like 6 missed updates, and then it keeps information around for a while. So it can take, in the order of magnitude of several minutes for failures to be detected and corrected in RIP. It also uses hop count for its metric regardless of link speed. So RIP would prefer 1 hop over a 56K line instead of 2 hops over 10 gigabit links. So as far as RIP is concerned, if you're using a network that has what's the word I'm looking for? Different. I was trying to think of the fancy word for different link speeds. You don't want to use RIP because it won't necessarily always pick the fastest link. So, in summary, RIP doesn't pick the optimal path based on bandwidth and is slow to detect and correct failures. So, I would probably never actually use RIP in the real world for any reason. So, we just kind of use it for comparison's sake and to show what a bad routing protocol looks like, I don't know if I should say bad. It's just misunderstood. Here's how you're going to configure RIP. I showed the routing table. The router is actually already configured for RIP before I configured it for RIP. The routing table shows that it's configured because it already has the R's. If your router is not configured for RIP, even if the other routers you're connected to are configured for RIP, you're not going to accept that information from those other routers. So this routing table shows the already configured routes, but this is the steps you would run to configure RIP. You type conft to get into config mode, router RIP, version 2. We want to always use version 2 because it is classless. Version 1 was classful. And then you put the network commands for the directly connected networks. Right, so in this case, we have a C for 1.0, we put 1.0. We have a C for 11.252, we put 11.252. No, wait, we didn't. We put 11.0. Well, if you actually put 11.252, when you look at your config, it only has 11.0 because the config takes a classful network as its argument. So even if you put 11.252, it will accept that command, but when you look at the running config, it's going to say 11.0. It's just the way it does it. We have a connected route for 21.0, so we put a network statement in for 21.0. Lots of times people want to put in network statements for every network in the inner network. So in this case, we know there's a 22.0 somewhere, we know there's a 12.0 somewhere, we know there's 11.0/27. Sometimes people want to put all those in. You do not need to put all those in. Only put in networks that you're connected to. OSPF stands for Open Shortest Path First. It is considered a link state routing protocol. The metric is a cost based on the interface speeds. The cost for the entire route is the sum of the interface speeds. How does a link state OSPF protocol work? Each router initially sends a link state advertisement packet that gets flooded to all the other routers. Once all the routers have received all the link state advertisements, each router will independently run Dijkstra's algorithm, which is also known as the shortest path first algorithm, and build its routing table. So basically, the router says, "Oh, let's see. Let me find my shortest path I have." So it's like, okay, it takes me 12 to get to router A, and 14 to get to router B, and 16 to get to router C. I'm going to go ahead and put router A and 12 in my routing table, and then it just continues running through that until it's added every node to the table. Convergence is fast for OSPF. Changes generate new link state advertisements immediately, and the routers rerun the SPF algorithm anytime they get the new LSAs. OSPF can be more complex to configure. It does support this idea of multi-area configurations. Essentially, every router in an area will receive and process LSAs and run the SPF algorithm when it gets in an LSA. And if you have a large network that can be processing, that can consume a fair amount of processor power, so you can design your network to have multiple OSPF areas, and then each area is kind of insulated from the other areas. So if I have two areas and something changes in area 1, that will not necessarily require any changes to area 2 unless something changes that area 2 needs to know about. So multi-area configuration tries to lessen the processing burden on the CPU of the routers in other areas. How do you configure OSPF? Again, I'm showing an OSPF routing table first. You'll notice the O for OSPF, the administrative distance is 110 versus 120 for RIP. So OSPF is considered by the router to be a better routing protocol, a more reliable routing protocol. Here we have the metric, which is the cost. I have the cost of 2 for this network. I have a cost of 65 for these other networks, and a cost of 66 for those networks. So that's the cost. And then we have a next hop, a timer, and the interface to send it out. To configure OSPF, config T, conf T, configure terminal, whatever you want. Router OSPF 1, this 1 is the process ID. You can have different OSPF routing tables for different types of service, but that's beyond the scope of this course, so we're not really going to talk about that. And then you configure OSPF by providing some number of network statements. A network statement consists of a network address or IP address combined with a wildcard mask and an area specification. So in this case, I did it two different ways. This first set of 3 entries, I entered a individual command for each connected interface. So I said, hey, 192.168.1.0 with a wildcard mask of 0.0.0.255. That essentially says, look at the first three octets. Anything that matches, I want to enable OSPF on those interfaces. Same thing with 11.0 and 21.0. And then area 0, that's when you specify which area the router is in. So in this case, we only have area 0. If we had more areas, you'd see area 1 or area 2, stuff like that. Down here, the last statement, I used one network statement to enable all 3 networks. I used a 0.0.255.255 wildcard mask, which basically says only look at the first 2 octets. So in this case, anything that starts with 192.168 will be considered part of this OSPF config in area 0. EIGRP is a Cisco proprietary routing protocol. What that means is that you can only use it with other Cisco equipment. It's considered a balanced hybrid or advanced distance vector routing protocol. What that really means, I don't know. Distance vector is just hop count. Well, this routing protocol looks at each hop, but it does more than just consider whether or not there's a hop there. The metric is a composite of bandwidth and delay. What the heck does that mean? Well, I copied this algorithm formula. It says the metric equals 10 to the 7th over the least bandwidth divided by the least bandwidth, right? Plus cumulative delay times 256. So what we need to know is that it considers the actual speed of the link and how slow things are, and comes up with a number that it uses to build a routing table based on that number that represents a measure of the bandwidth and the delay. Convergence for EIGRP is fast. In many cases, it pre-selects the next best route. So it already knows what it's going to do if a route fails. So it's like, oh, hey, that link went down that I was sending traffic out. I need to start sending it out this other side. And it's like fast. Configuring EIGRP. First, let's look at the routing table. For EIGRP, the symbol is a D. For EIGRP, we have some D's in here. If we look, the administrative distance is 90, right? So 110 for OSPF, 120 for RIP. EIGRP is 90, so routers prefer EIGRP to both OSPF or RIP. This next value is the metric 2174-2172-416, which is the whole bandwidth and delay thing, and then the next hop in the interfaces. Configuring EIGRP, similar to OSPF router, EIGRP1, we got to specify, I think they call it an AS number for EIGRP. Maybe it's a process ID, I can't remember. And then we need to do network statements. In this case, I had connected networks in the 140.1 network. I had 140.1.1, 140.1.2, 140.1.3. I represented all of those with this network 140.1.0.0 with this wildcard mask that said, okay, only worry about the first 2 octets. There's no area with EIGRP. No need to worry about that. And I had one other connected network, 192.168.1.0, so I put that in with that wildcard mask, and that would take care of the EIGRP configuration. So I didn't really talk about BGP, and that was intentional at this point. I don't want to muddy things. We're going to be doing a IGP lab exercise where we worry about internal routing. We're not worried about external routing yet. We'll probably worry about that when we get to the project at the end of the semester. But for now, that was just a quick overview of routing protocols, static routing, dynamic routing, and the protocols we're likely to see in class. So to summarize, EIGRP is probably the fastest, but it is Cisco proprietary. OSPF is pretty good protocol that you can use between different vendors, and RIP is terrible, and I would never use RIP in the real world. Any questions? Put them on the discussion board, bring them to class.